Imagine you're deploying a smart factory full of ESP32 sensors measuring temperature, vibration, and humidity. Each sensor must send data reliably without draining its battery or overloading the network. The choice of communication protocol can make or break the setup. In this lesson, we'll focus on two protocols: HTTP, the backbone of the web, and MQTT, designed specifically for IoT. HTTP is simple and integrates easily with cloud APIs, but it carries heavy overhead. MQTT, on the other hand, uses a publish-subscribe model that's lightweight and efficient. By comparing their architectures, strengths, and limitations, you'll see exactly where each one fits. You'll also learn how some systems combine them for both efficiency and compatibility. By the end, you'll be equipped to choose the right protocol for your ESP32 projects, ensuring reliable, efficient communication that scales with your IoT needs. HTTP, or Hypertext Transfer Protocol, is the foundation of the web. It works on a simple request-response model. A client sends a request, and the server replies. In IoT, your ESP32 often acts as the client, sending sensor data to a web server or fetching configuration updates. Each transaction includes a TCP handshake and headers, which can be larger than the actual data. For example, 20 bytes of sensor data might require 200 plus bytes of HTTP overhead. This makes HTTP inefficient for frequent communication but perfectly fine for occasional tasks. Its real advantage lies in compatibility. Nearly all cloud services, dashboards, and APIs support HTTP. So if your ESP32 only needs to upload data occasionally, like a smart meter sending a daily report, HTTP works well. But for rapid, continuous updates, its heavy overhead drains power and clogs the network. Let's weigh HTTP's pros and cons for IoT. On the plus side, HTTP is everywhere, easy to test with tools like Postman or curl, and most dashboards and APIs already use it. It's human-readable and straightforward for developers. But the downsides are serious for IoT. Each request creates overhead that quickly drains battery-powered devices. Even with persistent connections, HTTP consumes more energy compared to MQTT. Polling for updates is another issue. The ESP32 must repeatedly ask the server for changes, wasting bandwidth and time. This approach doesn't scale well when hundreds of devices are involved. For occasional reporting or configuration, HTTP is fine. But for frequent telemetry or low-power sensors, it quickly becomes inefficient. In other words, use HTTP when universality and simplicity matter more than efficiency, but don't rely on it for real-time, continuous IoT communication. MQTT, or Message Queuing Telemetry Transport, was built for IoT. Instead of request response, it uses a broker-based publish-subscribe system. Devices publish data to topics, and subscribers automatically receive updates without polling. This design reduces traffic and latency while allowing devices to conserve energy. For example, an ESP32 sensor can wake up, send a message, and return to sleep. MQTT also supports QoS, quality of service, levels, letting you choose how reliable delivery should be. Imagine it like subscribing to a magazine. You don't call the publisher every day, you just get the issues delivered when they're available. This makes MQTT perfect for environments where data flows frequently, networks may be unstable, and battery life matters. That's why it dominates smart homes, industrial monitoring, and agriculture. The MQTT architecture centers on the broker. Think of it as a post office that routes messages. Devices publish messages to specific topics like factory sensor 1 temp, and any subscriber to that topic instantly receives the update. Publishers and subscribers don't need to know about each other. They only interact with the broker. This decoupling makes systems scalable and fault-tolerant. Brokers like Mosquito, open source, or cloud services such as AWS IoT Core can handle thousands of simultaneous connections. They also buffer messages if subscribers go offline temporarily, ensuring data isn't lost. For ESP32 devices, this means simpler code and more efficient communication. Organizing topics hierarchically allows clean system design, like grouping sensors by floor, building, or device type. Security is also built in, with options for authentication, encryption, and access control. MQTT introduces quality of service, QoS, to guarantee message delivery even on unreliable networks. There are 3 levels. QoS 0, at most once messages are sent without confirmation, fast but not guaranteed. QoS 1, at least once messages are acknowledged, ensuring delivery but risking duplicates. QoS 2, exactly once, the most reliable, ensuring each message arrives only once but with more overhead. This flexibility allows you to match reliability to your application's needs. For instance, an ESP32 soil sensor may use QoS 0, since losing one reading isn't critical. But an emergency alarm must use QoS 2 to avoid duplicates or loss. HTTP, by contrast, only guarantees delivery through TCP acknowledgement and lacks such flexibility. For IoT, MQTT's QoS ensures data integrity even under poor network conditions. One of the biggest differences between HTTP and MQTT is message overhead. HTTP transactions require handshakes, headers, and status codes, meaning that a tiny 20-byte sensor reading could expand to 500 bytes. In contrast, MQTT adds only a small 2-byte header plus topic and payload, making it much more efficient. This has huge implications for battery and bandwidth usage. An ESP32 sending one reading every second via HTTP would quickly drain its power source and clog the network. With MQTT, the same device could operate efficiently for weeks or months. HTTP has tried to adapt with persistent connections in HTTP 1.1, multiplexing in HTTP 2, or WebSockets. But these still consume more resources than MQTT's lean design. For constrained IoT devices, MQTT's efficiency often means the difference between a practical deployment and a failed one. Despite its inefficiencies, HTTP still plays a valuable role in IoT. It shines when devices need to interact with web platforms, APIs, or dashboards. For example, an ESP32 thermostat can use HTTP Post to upload a daily energy report, or use HTTP GET to download firmware updates. HTTP is also ideal when humans interact directly, such as checking device status from a mobile app. Its universal support means developers can integrate IoT data into existing systems without extra effort. But remember, HTTP works best when communication is occasional, not continuous. Using it for high-frequency telemetry would waste energy and clog the network. So in IoT, HTTP should be seen as a bridge to web services, not the backbone for real-time data exchange. MQTT is the protocol of choice for scenarios needing frequent updates and real-time responsiveness. In industrial automation, sensors stream vibration and temperature data every second to monitor equipment health. In smart homes, MQTT powers devices like switches, lights, and motion detectors, enabling instant reactions to user actions. In agriculture, ESP32-based soil and weather sensors publish frequent updates, ensuring irrigation responds automatically to conditions. MQTT's many-to-many model means one device's data can be consumed by multiple subscribers at once, such as analytics platforms, dashboards, and actuators. Its small packet size and sleep-friendly design make it ideal for battery-powered devices. Combined with QoS, MQTT provides both speed and reliability, even when networks are unstable. For IoT ecosystems requiring constant communication, MQTT is the clear winner. In real-world IoT systems, HTTP and MQTT often work together rather than competing. MQTT usually handles telemetry and control, while HTTP supports configuration and cloud integration. For example, an ESP32 soil sensor could publish real-time moisture readings via MQTT to a local broker controlling irrigation pumps. At the same time, it could send daily summary reports via HTTP to a cloud dashboard for analytics. This hybrid model offers the best of both worlds. MQTT provides efficient, low-latency communication, while HTTP ensures easy integration with web services. Designing such systems requires synchronization and consistent security policies across both protocols. If done right, combining HTTP and MQTT results in robust, scalable, and interoperable IoT architectures that balance efficiency with accessibility. Before choosing a protocol, reflect on your project needs. How often will your device transmit data? If it's every few seconds, will HTTP's overhead waste too much energy? If the network is unreliable, can MQTT's QoS levels prevent data loss? Would a hybrid model, MQTT for real-time control, HTTP for reports, serve better? Also, think about scalability. Will your project grow to hundreds or thousands of devices? HTTP servers may struggle, while MQTT brokers scale more smoothly. Finally, consider your team's expertise. If your developers are comfortable with REST APIs, HTTP may be easier to start with. But for long-term IoT deployments, MQTT's publish-subscribe model is often the better investment. Reflecting on these trade-offs ensures your ESP32 projects are efficient, reliable, and future-proof. In this lesson, you explored two major IoT protocols, HTTP and MQTT. HTTP, with its request-response model, excels in simplicity and web integration but struggles with frequent telemetry due to overhead. MQTT, with its broker-based publish-subscribe model, minimizes bandwidth, supports device sleep cycles, and offers QoS for reliable delivery. We compared their strengths, weaknesses, and practical applications, from smart meters and firmware updates with HTTP to industrial sensors and smart homes with MQTT. You also saw how combining both can create powerful hybrid systems that balance efficiency with interoperability. By now, you should be able to evaluate your ESP32 project's requirements and choose the right protocol or combination. This foundational knowledge will help you design IoT systems that are robust, scalable, and energy efficient, ready to support real-world applications.